Okay, so now let's talk a little bit about exercise 14.4. Exercise 14.4, and that is question number 1. You want to rewrite this statement that I will just write with if then. Rewrite with if then in 5 different ways. Different ways conveying the same meaning. So about if then, we said that basically now what we had before was basically an example, and we said that basically there are several ways of understanding if P then Q. If P then Q statements. We shall illustrate these ways in the context of the following statement. And we had some statement over here which was R, and R was basically if a number is a multiple of 9, if a number is a multiple of 9, then it's a multiple of 3. Then it's a multiple of 3. It's a multiple of 3. Now let P and Q denote these two statements. P denotes a number is a multiple of 9, meaning that this is this first statement over here. A number is a multiple of 9, and Q is the statement a number is a multiple of 3. And then we said that if P then Q, and if I have these two, basically if I have P over here and Q over here, then if P then Q, meaning that if I say if a number is a multiple of 9, then the number is a multiple of 3, that is the same as the following. And we had basically 5 different ways of understanding that. Number one, we said that first of all, P implies Q. First, P implies Q, and this is denoted by P implies Q. Now what this means, if I say P implies Q, what this means is that a number is a multiple of 9. So P was a number is a multiple of 9. Q was basically a number is a multiple of 3. So this says that the number is a multiple of 9 implies that it's a multiple of 3. So that's basically the same thing, but just some sort of like something like a definition. Number 2. This was number 1, and number 2 was P is a sufficient condition for Q. P is a sufficient condition for Q. Now what that means is that knowing that the number is a multiple of 9 is sufficient to conclude that the number is a multiple of 3. And number 3 was P only if Q. P only if Q. What that means is that basically a number is a multiple of 9 only if the number is a multiple of 3. So P was basically basically P that we have over here was that the number is a multiple of 9, and Q was a number is a multiple of 3. So P only if Q means he basically says that a number is a multiple of 9 only if it's a multiple of 3. So this is still easy to understand, and Q is a necessary condition for P. So over here we said that P is a sufficient condition for Q, and then on the other hand you can say that Q is a necessary condition for P. So for Q is a necessary condition for P. Necessary condition for P. So I think I said something in the previous video that based on this is, now that I think about it, was actually logically wrong regarding the necessary condition and sufficient condition. So again, in this context, if you say that your statement P is a number is a multiple of 9 and Q is a number is a multiple of 3, then you can say that P is a sufficient condition for Q. P is a sufficient condition for Q, meaning that if you know that a number is a multiple of 9, it's enough to conclude that the number is a multiple of 3. And also you can say that Q is a necessary condition for P, meaning that when a number is a multiple of 9, it is necessarily a multiple of 3. So when you say Q is a necessary condition for P, well, it does have the name condition, but it's actually not much of a condition in the sense that we understand the word condition. Meaning that when you say Q is a necessary condition for P, what that means is that basically when you know that the number is a multiple of 9, it is necessarily then a multiple of 3. So that's what that means. And also number 5, we said that not Q implies not P. Meaning that if a number is not a multiple of 3, it's not a multiple of 9. Okay, so that's the example that we had. Now this was the example that we had. Now what we have over here as the question in exercise 14.4 is basically if a natural number is odd, if a natural number is odd, then its square is also odd. Then its square is also odd. Now I don't know really if that's true or not. So for example, 3 squared is equal to 9. Then for example 5 squared is equal to 25. 7 squared is equal to 49. Seems to be true. 9 squared is equal to 81. 11 squared is equal to 121, and so on and so forth. So it seems to be true. Now, so now the sentence that we have is, if a natural number is odd, then its square is also odd. Now you want to rewrite this statement with if then in 5 different ways conveying the same meaning. So the first way that you can write it is that I'm just going to write from the solution, because I'm learning too. So it says that a natural number is odd implies that its square is odd. That's basically the first way that the first thing that we set here. P implies Q is denoted by P implies Q, and that what that means is that, well, P implies Q. So in the case of this example, I can say that a natural number is odd a natural number is odd implies that its square is odd. Implies that a square is odd. Okay. What that means, we will understand based on the next 4 examples. The next 4 ways, basically. Okay, so now the second way that we can understand P implies Q, basically we can say that natural number is odd only if its square is odd. So there is basically this part which we talked about, only if. So that's basically part 3. So I can say that a natural number is odd. A natural number is odd only if its square is odd, which is of course something which is, well, at least I'm not very used to thinking that way about if-then clauses or if-then statements, but that's actually the case, which is, you can say that a natural number is odd only if its square is odd. Number 2, and this is let's call this number 1 and 2 for the sake of simplicity. Number 1 and number 2, let's say, or let's put them, let's write them this way. I am going to write them this way. 3 as natural number is odd. I'm going to write a natural number is odd only if its square is odd. Only if its square is odd. And then about this case, what we said was that let me find that place over here. Now this says that the number is basically, well, it's just the same thing. A natural number is odd only if its square is odd. That means that well, there is no way to make any, I mean, you can of course make sense of this statement, but you need to be cautious. So you can make sense of this statement very cautiously, meaning that you can say that the natural number is odd only if its square is odd, but I'm not really sure exactly how I should make sense of this statement, so I just keep it as it is. Okay. Now number 2, based on number 2 over here, I can say that P is a sufficient condition for Q, meaning that I'm going to say that necessary. So over here, this is number 4, for the square of a natural number to be odd. For the square of a natural number to be odd. So here it says that if a natural number is odd, then its square is odd, right? So I can say that for the square of a natural number to be odd, it's sufficient that the number is odd. So that way I can write it. I can write for the square of a natural number to be odd, for the square of a natural number to be odd, for the square of a natural number to be odd, it is sufficient that the number is odd. It is sufficient that the number is odd, meaning that basically P is a sufficient condition for Q, right? P is a sufficient condition for Q. In this context, what it means is that for the square of a natural number to be odd, it is sufficient that the number is odd. Okay? And number 4, we said that Q is a necessary condition for P, meaning that over here what that means is that if a natural number is odd, then its square is necessarily odd. That's how you can say it. So for a natural number to be odd, it is necessary that the square is odd. So you can write for a natural number to be odd, for a natural number to be odd, it is necessary that its square is odd. That its square is odd. And number 5, we said that basically not Q implies not P, meaning that if the square of a natural number is not odd, then the number is not odd. So if the square of a natural number is not odd, then the natural number is not odd. So that way you can write it. Number 5, if the square of a natural number is not odd, then the natural number is not odd. Then the natural number is not odd. So that's basically question number 1. And this is, of course, very important. Now we had basically one chance of practicing it, but this must be practiced more and more in order in order for you to learn it, really. I don't think one example is enough, but for now it's all that we have. Now question number 2, we want to write the contrapositive and converse of these statements. So for example, we have a statement: if x is a prime number, if x is a prime number, then x is odd. If x is a prime number, then x is odd, which is not true. Of course, it's not true because 2 is a prime number, but it's even. So, but now to write the contrapositive of this statement, what you can say is that, well, if you take this as p, meaning that p, you can take it as x is a prime number. And q, you can say x is odd. Now to write the contrapositive of this, you have to write if not q, then not p. That's basically the contrapositive of this. Meaning that you need to write basically if x is not odd, so then the contrapositive becomes if x is not odd, then x is not a prime number. Then x is not a prime number. Okay? And the converse of this, if this is p and this is q, the converse would be basically if p, then q, then the converse of that would be if q, then p, right? That is the converse. So then for the converse, I need to write if x is odd, then x is a prime number. If x is odd, then x is a prime number. Okay? If x is odd, if the number x is odd, then it's a prime number. That is question number 1. I'm sorry, the part 1 of question number 2. Now, part 2 of question number 2 is a statement which says if two lines are parallel, or if two lines are parallel, if two lines are parallel, then they do not intersect in the same plane. Then they do not intersect in the same plane. Now the contrapositive of this would be if not q, then not p. So the contrapositive would be if okay, so then the contrapositive of this statement would be if two lines do not intersect in the same plane, intersect in the same plane, if two lines do not intersect in the same plane, then they are not parallel, and the converse is that. If two lines intersect in the same plane, that's actually the answer that you have in the book is wrong. You have to say if two lines do not, that's do not intersect. Okay. So basically, if two lines intersect, you have to write the negation of this statement, meaning that you say that if two lines instead of do not intersect, you have to say intersect in the same plane, then they are not parallel. Then they are not parallel. And the converse of this would be if two lines do not intersect in the same plane, if two lines do not intersect in the same plane, if two lines do not intersect in the same plane, then they are parallel. Okay. So the next example that we have is something is cold implies that it has low temperature. So you have something is cold. Something is cold implies that it has low temperature. So something is cold implies that it has low temperature. So then the contrapositive of this would be if something does not have low temperature, that implies that it is not cold. That's something like that. Or you can say that if something is not at low temperature, then it's not cold, something like that. If something is not at low temperature, if something is not at low temperature, then it's not cold. Then it is not cold. And the converse of this would be if something has low temperature, if something is at low temperature, If something is at low temperature, then it is cold. I suppose that's how you write it. If something is at low temperature, then it is cold. So that is that. And then you cannot comprehend geometry if you don't know how to reason deductively. You cannot comprehend geometry if you cannot reason deductively, which is of course very true. You cannot comprehend geometry if you cannot reason deductively. Now I suppose you should rewrite this sentence as if you cannot reason deductively, if you cannot reason deductively, you cannot comprehend geometry. Okay, so basically all I did was that I put this if clause in the beginning, and then the then clause put it over here. So I haven't changed this thing at all yet. So now the contrapositive in this case is if you basically the contrapositive is if basically not Q, then not P, right? Then not P. So now this is your P, this is your Q. So if not Q would be if you can comprehend geometry, the contrapositive, if you know how to reason deductively, right? Well, if you know how to reason deductively, so what they have done, they haven't rearranged this thing yet all. So let me do the same thing. They have not rearranged this. I thought I should do that, but they haven't. So again, the contrapositive is basically if not Q, then not P, right? Not P. So what that means is that if not Q, meaning if you can reason deductively, or as written here, if you know how to reason deductively, if you know how to reason deductively, then you can comprehend geometry. So here you have you cannot comprehend geometry. The negation of that would be then you can comprehend geometry. basically the converse of this is basically it says that you cannot comprehend geometry if you cannot reason deductively. So the converse of this is you cannot reason deductively if you cannot comprehend geometry. If you don't know how to reason deductively, then you cannot comprehend geometry. So if you don't know how to reason deductively, if you don't know how to reason deductively, you cannot comprehend geometry. You cannot comprehend geometry. Okay, so that is that. Now the next question that we have is x is an even number implies that x is divisible by 4. X is an even number implies that x is divisible by 4. So x is an even number implies that x is divisible by 4. So what this means is that this is your if clause, and implies means that basically this notation over here. So that means that if this, then that, right? So the contrapositive of this would be if not q. So if x is not divisible by 4, if x is not divisible by 4, then x is not an even number. Then x is not an even number, which is of course not true, but that's the contrapositive, meaning that the statement itself is not, of course, true, because it says that x is an even number implies that, meaning that if x is an even number, then x is divisible by 4, which is divisible by 4 means that basically x is a multiple of 4. Well, kind of what it has to be, basically a number which is divisible by a number, and an even number has to be actually divisible by 2, because then you would lose some numbers there. But anyway, that's not the point here. The point is to find the contrapositive, and for the contrapositive you say that if not q, then not p, meaning that if x is not divisible by 4, then x is not an even number. So here we have, can be written as if x is an even number, then x is divisible by 4, okay? And the contrapositive is if x is not divisible by 4, then x is not an even number. That is correct. And the converse is if x is divisible by 4, if x is divisible by 4, meaning that you have to write if q then p. If q then p. If x is divisible by 4, if x is divisible by 4, then x is an even number. Then x is an even number. Now the point of these exercises is not whether the statement is true or false. The point is to understand basically the concept of contrapositive and converse. Otherwise we will have other things later related to contrapositive and converse. We will use them in the algebra of logic later, right? So question number 3, we have write each of the following statements in the form if then. So you want to write these statements in the form if then. You get a job implies that your credentials are good. So to write this in if then form, what you need to do is, for example, you can write this as if you get a job implies that your credentials are good, meaning that if you get a job, number 1, if you get a job, then your credentials are good. Then your credentials are good. So number 1, if you get a job, then your credentials are good. Number 2 is the banana tree will bloom if it stays warm for a month. So the banana tree will bloom if it stays warm for a month. So then you can say if it stays, so then you can say that if it stays warm for a month, if it stays warm for a month, then the banana tree will bloom. Then the banana tree will bloom. If it stays warm for a month, if the banana tree stays warm for a month, then it will bloom. What they have written, it, of course, the sentence is not wrong. What they have written in a slightly different way, the meaning, I mean, as far as writing the sentence in if then, in if then form, our answer is not wrong. Meaning logically is not wrong, although they have written it in a slightly different way, which is not a problem. And number 3 is a quadrilateral is a parallelogram if its diagonals bisect each other. So let me write the sentences over here, because that way you might not understand me reading the question. So the question is a quadrilateral is a parallelogram if its diagonals bisect each other. If its diagonals bisect each other. So you can say that a parallelogram is a quadrilateral is a parallelogram. So you can say that if the diagonals of a quadrilateral bisect each other, so then you can write this sentence as if the diagonals of a quadrilateral bisect each other, then it is a parallelogram. Then it is a parallelogram. If the diagonals of a quadrilateral bisect each other, then it's a parallelogram. Number 5 is to get an A+ in the class. It's necessary that you do all the exercises of the book. So to get an A+, in the class, it is necessary that you do all the exercises of the book. That you do all the exercises of the book. So that means that if you do all the exercises of the book, then you will get an A+ in the class. So you can write so when you say it is necessary, that is a condition. So then you can say if you do all the exercises of the book, then you will get an A+ in the class. So or what they have written is if you get A+ in the class, then you do all the exercises in the book, which makes no sense. What they have written is basically to get an A+ in the class. Of course, logically, what they have written is, of course, right, because basically what happens is that in the case of if-then clauses, we said that, let me see. So basically, in the case of if-then clause, in the case of if-then, meaning that we said that if P then Q, when you have if P then Q, then that basically means that P implies Q, which is the same thing as P implies Q. Now what this means is that P is a sufficient condition for Q. P is a sufficient condition for Q. Meaning that, for example, in the case of that example that was about basically a number a multiple of 9 and a number of multiple of 3. P was basically a number is a multiple of 9, and Q was a number is a multiple of 3. Now, if P is a sufficient condition, if P is a sufficient condition for Q, that means that knowing that the number is a multiple of 9 is sufficient to conclude that the number is a multiple of 3, right? So then if you bring the same concept over here basically the sufficient condition here is that you do all the exercises of the book to get an A in the class. That means that you have to say if you do all the exercises of the book, then you will get an A plus in the class, which is what I have written over here, but they have written the converse of this, or they have written the same thing in the reverse order. Now this, we had some other part over here that says P only if Q. That means that this says that the number is a multiple of 9 only if it is a multiple of 3. P only if Q, meaning that the number is a multiple of 9 only if it's a multiple of 3. So then over here, the same concept, you will get an A in the class only if you do all the exercises in the in the book. That means that if this is done, that the number is a multiple of 9 only if it is a multiple of 3. Well, to me that's two different things. So P is a sufficient condition for Q, meaning that this says that knowing that a number as a multiple of 9 is sufficient to conclude that it's a multiple of 3, which makes sense, okay? Now, if P only if Q says that a number is a multiple of 9 only if it is a multiple of 3. And then also Q is a necessary condition for P, meaning that when a number is a multiple of 9, it is necessarily a multiple of 3. Now, which one do I... So let's see what we can do with this. So basically we have P implies Q. That's the same thing as if P then Q, right? Now when you have this, there are 3 different things here that we need to understand. So the first thing is that P is a sufficient condition for Q. P is a sufficient condition for Q. Now what this means in the context of that example that we had before, meaning that if you take P as and basically a number is a multiple of 9 and Q a number is a multiple of 3, right? So if you have that example in mind, P is a sufficient condition for Q means that knowing that a number is, and write it basically in this form, meaning that knowing that the number is a multiple of 9 is sufficient to conclude that it's a multiple of 3, which makes sense, okay? Now, the second part of them, or the second way to understand this, is to say P only if Q. P only if Q, which I don't understand. It says that this says that the number is a multiple of 9 only if the number is a multiple of 9 only if it's a multiple of 3. And the third part is Q is a necessary condition for P. Now this says that when a number is a multiple of 9, it is necessarily a multiple of 3. But I have some problem with this. Maybe I haven't understood it properly or completely. But let's see. So let's say that you have, to get an A plus in the class, it is necessary that you do all the exercises of the book. To get an A plus in the class, it is necessary that you do all the exercises of the book. Well, you know, I'm not going to answer this question. I'm going to leave it for later. Hopefully later we will understand it. But for now, I simply don't understand it. Okay, so question number 4 is, given statements in A to B, identify the statements given below as contrapositive or converse of each other. So you have A and B. So that the first question is, if you live in Delhi, in Delhi, or New Delhi in India, then you have winter clothes. Then you have winter clothes, because it's kind of cold there compared to, for example, south of India. Now, this is A, and number 1 is, if you do not have winter clothes, then you do not live in Delhi. And number 2 is, if you have winter clothes, then you live in Delhi. Okay, so the main basically statement that we have is, if you live in Delhi, then you have winter clothes. Now this statement number 1 says that if you do not have winter clothes, then you do not live in Delhi, which is the contrapositive of A. Which is the contrapositive of A. And the second one says that if you have winter clothes, then you live in Delhi, which is the converse of A. Which is the converse of A. So the first one is contrapositive converse. The second question, or the second statement, is if a quadrilateral is a parallelogram, if a quadrilateral is a parallelogram, if a quadrilateral is a parallelogram, then its diagonals bisect each other. Then its diagonals bisect each other. Now this is A, this is B, and then number 1 is if the diagonals of a quadrilateral do not bisect each other, if the diagonals of a quadrilateral do not bisect each other, then the quadrilateral is not a parallelogram. Okay, and number 2 is if the diagonals of a quadrilateral bisect each other, then it is a parallelogram. Okay, so the question here is if a quadrilateral is a parallelogram, then its diagonals bisect each other. The first sentence over here says if the diagonals of a quadrilateral do not bisect each other, then the quadrilateral is not a parallelogram, which is the contrapositive of B. Which is the contrapositive of B. This is the contrapositive. And here we have if the diagonals of a quadrilateral bisect each other, if the diagonals of a quadrilateral bisect each other, then it is a parallelogram, which is the converse of B. So that's contrapositive and converse. Okay, so the next part that we have here is about validating statements. So we have a couple of things here. There's some rules and by contradiction, and some exercises and some miscellaneous examples. Okay, so there is still a couple of things here to discuss, but in the next video we will talk about validating statements. So I'll see you in the next video. Thank you.